Yes, sir. Now the recording is started.
Okay. So let me start by welcoming today's speaker, Professor Govind Krishnaswamy. So let me first say good afternoon to everyone in this audience, online audience. I'm very happy to welcome all of you on behalf of Professor Sendil Velen, who is away in some official meeting, to this 26th lecture in the lecture series on nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharatdasan University, with the support of RUSA 2.0. Now it's a great pleasure to introduce the audience today's speaker, Professor Govind Krishnaswamy from Chennai Mathematical Institute, Chennai. Govind is quite well known to me for several years. We have participated in several lecture workshops in different parts of Tamil Nadu. And I always admire him, admire his lectures. Its clarity, its lucidity, and the way every time it reminds me of Professor Mugunta. Not only in his personality, but also the way in which he lectures. It's really Govind. So all those lectures I really enjoyed, and some of your lectures online also I have enjoyed very much. Now, for the benefit of our MSc students and young researchers and the participants from outside the university, let me give a brief account of some of the academic details of Govind Krishnaswamy. Govind obtained Bachelors of Science in Physics and Bachelor of Arts in Mathematics to start with, and then Master of Arts in Physics. He completed his PhD at the University of Rochester, USA, and then carried out his postdoctoral studies in Netherlands and UK. Then in 2010, he joined Chennai Mathematical Institute, where he is now a full professor. Govind works on several areas of physics and interesting topics, including quantum field theory, particle physics, fluid and plasma dynamics, and of late in nonlinear dynamics. He has won several awards. To name a few, I can say Arthur Gale Prize, Apcar Award from American Physical Society, Marie Curie Fellowship, and Ramanujan Fellowship. When Sendil Velen invited him to deliver a lecture at this forum, he immediately agreed. And the Department of Nonlinear Dynamics is very much thankful for his acceptance. With this short introduction now, I hand over the session to Professor Govind Krishnaswamy for his lecture on chaos in three-rotor problem. Govind, it's all for you.
Okay. So thank you very much, Professor Lakshmanan, for this very kind and kind invitation, as well as introduction, as well as to Professor Sendil Velen, who is busy at another meeting, I understand, just now. Yeah, so this is a lecture on at Bharatdasan University, of course, though we are all in various places. I have been to Tiruchi and gone up the rock fort, but yes, but I'm not there right now. I hope to come there sometime. So this work is this talk is based on work with Himalaya Senapati, who is a PhD student who just recently graduated, and Ankit Yadav, who is a current graduate student working with me at the Chennai Mathematical Institute. So it is based on these three papers primarily. So these two are research articles in the journal Chaos. And then there is this expository article in the magazine Resonance, journal Resonance, introducing some aspects of the three-body problem. So my aim here is not to tell you everything that we have done, but just to introduce some of the terms and motivate the problem and explain some of the ideas. So please feel free to interrupt me. So what is the three-rotor problem? So the way I would like to view this problem for this talk is that it is simply a model system which we can use to study nonlinear dynamics and some other topics in physics. And by studying an example in detail, we learn many interesting phenomena and features of this model. And we can try to mimic some of the features that have been discovered in other places and see what they say here. This is the kind of game.
Govind, let me interrupt you for a moment. Can you come in the full screen mode, because it's not completely. It's part of the screen only we can see. Can you go to the full screen mode?
Well, actually, in this presentation, I am not sure how I can. Yeah, this is looks like the best I can do. Yeah,
I think that's fine. That's fine. I think.
Yeah, perhaps yeah. This is the maximum I can do. I think. Let me see. Can I do any better?
There should be on the top view, view, and then if you go to view, perhaps and see.
Yeah, I know what you mean.
Yeah.
But unfortunately, this doesn't have those options at all. So yeah. May I request, maybe in your reception, you can ensure that only my screen is enlarged, perhaps?
Is that okay? I think we can manage, so no problem. Please go ahead. I can read. I have no problem.
Okay.
Yeah, but some people may be using mobile, so in that case, please.
Okay.
But I think it's okay. Yeah, please go ahead. Yeah.
Sorry. Tell me, is this enlarged? You can see an enlarged version now, right?
Yeah, but part of the slide.
Yeah. So yes, no. So when necessary, I will enlarge things as and when necessary. Okay. So so here we are. What is the three-rotor problem? Now we have in mind, for simplicity, three equally massive point particles, and rotors is just a fancy name for them, primarily because they move on a circle. Yeah, so you have three equally massive point particles moving on a circle. So here is 1, 2, and 3. Yeah, they are distinguishable particles, but they have the same mass, and they move on this circle. They interact with each other through attractive cosine potentials. So if the coordinate of one of the particles is θ1, θ2, and θ3, then then the potential between the particles depends on the cosine of the difference in the angles, θ1 minus θ2, for instance. So, and there is some coupling constant which I can call G in front of that. So when the particles come close to each other, this potential becomes cosine of 0. That's 1. It has a maximum. So the force vanishes when the particles come close to each other. And it is oscillatory. Yeah, I mean, when they get farther apart, the force grows. The force is attractive because G is positive and things are set up so that it's attractive. And they move without collisions. What that means is they can basically pass through each other. These are particles of a strange sort. They are not extended particles like billiard balls, which would collide. Here, these are point particles, and they can move through each other. And I will explain why that is physically reasonable by connecting it to another problem of physics. Yeah. So to get some understanding of the kind of dynamics one actually sees, let me give you a movie of a dynamics of this system. So in this movie, you see these 3-point particles, and they're exaggerated by making them a little bit like disks. They move around a circle. They don't move uniformly because there's forces between them, the cosine of the interparticle displacement. Yeah. So each particle feels a force due to both the others. So cosine θ1 minus θ2 and cosine θ2 minus θ3, both are involved. So one could, of course, consider more than 3 particles. You could have 4 particles on a circle, 4 rotors, in which case we would usually, in the context that I am discussing, θ1 would interact with its neighbors, namely θ2 and θ4. They're around a circle, so θ4 is like the last one, and also the 0th one. Yeah. So, but here, because there are just 3 of them, everybody interacts with everybody else. Yeah. So you clearly see that they can pass through each other without any collisions happening. Particles can reach turning points. Yeah, they can. The red one reached a turning point momentarily at rest and then return. So this is the type of motion one can see. But this is a relatively regular motion. There is more complicated things that can happen, which I will indicate as we go. Yeah. So to set up the problem, if the angular positions of the 3 rotors are called θ1, θ2, θ3, as I already mentioned, yeah, we have the so-called configuration space of this system. So each particle moves on a circle. So to specify the location of the first rotor, you need to give one angle, which is a point on a circle, and the circle is denoted S1. Yeah, S1 means a circle. So you need a circle's worth of information to locate the first particle, another circle's worth of information to locate the second particle, and similarly for the third one. And therefore, the configuration space is the Cartesian product of 3 circles. Okay, so so this is a 3-dimensional configuration space. It is simply the Cartesian product of circles. I mean, it's a lot like 3 particles, each of them moving on a line. Then you would have the Cartesian product of 3 lines, which would be the 3-dimensional Euclidean space. In this case, the 3-dimensional configuration space is called a torus. Yeah, a product of circles is called a torus. In this case, it's called a 3 torus because there are 3 circles. Okay. Now, to specify the dynamics, we write down the Lagrangian. So the total Lagrangian for the system is a sum I running from 1 to 3 of the kinetic minus the potential energies of each of the rotors. So the kinetic energy is simply given by half m r squared theta dot squared. So m is the mass of the rotor and r is the radius of the circle on which all of them are moving. Theta dot square is the square of the angular velocity. So that is added up for all the 3 rotors. Then you got some potential energies also. And I just described that. So the potential energy is cosine of θ1 minus θ2, and similarly cosine of θ2 minus θ3, and cosine of θ3 minus θ1. So you add up all of those cosine of differences. Yeah. And there is an 1 thrown in for sort of to make the energy zero when you're at the ground state. When all the rotors coincide, then all the angle differences will be zero. Cosine zero would be 1, and we want to cancel that 1 off, so that's why we put it there. Yeah. So the fourth rotor is the same as the first rotor. So we call that sort of periodic boundary conditions. They're just 3 rotors. Now I have described this system, and it's interesting in its own right, but it's connected to various other systems, which I should describe to you. I mean, one obvious case is that if you consider not 3 rotors but 2 rotors, it turns out that that problem is just 2 angular positions. That system is relatively familiar to us. It can be reduced to a very familiar system. Does somebody want to tell me which system is governed by a potential which is the cosine of an angular separation? Anybody would like to hazard a guess? Well, the pendulum, of course, there is a single particle, but the pendulum's potential energy is the cosine of its, it's proportional to the cosine of its angular displacement from equilibrium. Okay, so it turns out that the 2 rotor problem, upon going to sort of center of mass variables, can be reduced to a simple pendulum. So you can think of this 3 rotor problem as a generalization of the pendulum. A slightly more complicated version of the pendulum, well, much more complicated in some ways. Okay, and I also mentioned that there is no particular reason to stop at 3 rotors. You can add more of them. Now, another physical reason to be interested in this system is that the quantum version, so far I've been talking about the classical version, the quantum version models what are called chains of coupled Josephson junctions. Now, I'm not going to say much about this, except just introduce what a Josephson array, a chain of Josephson junctions is. So a Josephson junction is a junction or a sandip between 2 superconducting segments, metallic segments. So you have a superconductor here, another superconductor here, and they are separated by some non-superconducting material. Now, in each of the superconducting metallic segments, one learns that the degrees of freedom can be described using what's called a Landau-Ginzburg order parameter, and that is basically the wave function of Cooper pairs. And that wave function can be written as some kind of square root of the number density times e to the power of I theta. Okay, so this wave function of Cooper pairs in a superconductor can be written as the square root of a number density times a phase. I mean, after all, it's a complex valued wave function. Now that phase theta is called the superconducting conducting phase. Yeah. So associated to each of the superconducting segments, metallic segments, you have a phase. Okay, so the phase associated to this one is theta 3 and theta 2 and theta 1. So suppose you have 2 junctions, these 2, and you have 3 metallic segments. Yeah, of course you could add one more junction here and yet another metallic segment there with some theta 0 for perhaps. Yeah. Now Josephson discovered that due to quantum mechanical tunneling, these Cooper pairs can tunnel between these metallic segments, and that is part of this Josephson effect. Now, and you can string together many, form a chain of several of these junctions. Now, and this is of much interest. It is studied in condensed matter physics, low temperature physics, elsewhere. Now, the Hamiltonian for this system of Josephson junctions, chain of Josephson junctions, is given. I'm just going to state what it is. One needs to study where it comes from. There is a Josephson coupling energy across tunnel junctions. Okay, so it's called a tunnel junction because electrons can tunnel across the junction, and there is some energy associated with each tunnel junction, and that is given by some Josephson coupling energy Ej times the cosine of the difference of the superconducting phases in the adjacent segments, metallic segments. Okay, so you notice the similarity with our three-rotor problem. This cosine of the angular difference is coming from the Josephson coupling energy between metallic segments. In addition, there is a kind of capacitive charging energy, as I would like to call it, associated to each metallic segment. Okay, so this is part of each segment, and then you have the interface energy. I already talked about the interface energy, junction energy, but each metallic segment also has some potential, electric potential, and there is a capacitive charging energy associated to that, and that energy is essentially given by this Laplacian, the second derivative of the superconducting phase associated to that segment. So this second derivative operator, you can just think of it as minus d squared by dx squared, where x is replaced by an angle. So this operator will then go and act on the wave function, superconducting wave function. Yeah. So of course, in the classical theory, this kinetic energy becomes the usual kinetic energy theta dot squared. Yeah. This under the correspondence principle. Yeah. So I have tried to convey to you that the three-rotor problem may be viewed as the classical limit describing the dynamics of a chain of coupled Josephson junctions. Okay. So, and there is a dictionary you can set up between the parameters of the three-rotor problem, like this mass and radius and the coupling constant G, and the corresponding parameters over here, like the Josephson coupling energy and the capacitive charging energy, etc. And these chains of Josephson junctions can actually be fabricated in the lab and studied in great depth. And the reason I mention this is that though I do not do that, at least there is a way to study this system in the lab, and especially in the quantum case. This talk will be mainly focused on the classical theory. Yeah, quantum things I will not have, I do not intend to discuss here just yet. But the problem of full interest, at least in the low temperature physics setup, is the quantum one. But we can extract one more small piece of physics here, having to do with why the rotors could pass through each other without colliding. I mean, that is very peculiar. I mean, if particles come together, they would collide, or at least feel each other in some different way, you might think. Well, but when we view it as coupled Josephson junctions, it is quite okay for the superconducting phase in the third metallic segment to be the same as that in the second metallic segment. After all, there are two metals separated by some wafer. There is no particular reason why the superconducting phase here, when it happens to equal the one in the next segment, anything catastrophic should happen, like a collision between planets or something. Yeah? So unlike in the three-body problem of Sun, Moon, Earth, or asteroid and Jupiter, there is no concept of collisions here. Phases can be equal in neighboring segments, so particles can simply pass through each other. That is what we saw in the movie. Okay, so I have tried to give you a physical justification for this model. So rotor angles can coincide without any collisional singularities. Okay, so that is one motivation for this problem. There are other motivations. Let me, any question at this stage?
So there occurs no collision essentially because at the point of collision, the velocity becomes zero and continues the same sign, or something like that?
No, I wouldn't say the velocity becomes zero. If I go back to our picture, to our movie, the particles actually pass through each other at fairly substantial speeds. It is simply that the particles are not really physically on the same circle. These are really three different circles, one for each metallic segment. The three particles are moving on their own circles, but the circles are coupled to each other through the Josephson coupling energy. The representation through a single circle is only for our convenience.
Okay.
Yeah.
Okay.
Yeah. So we are reinterpreting the superconducting phase as the angular position of a particle. So, and through that reinterpretation, collisions between particles are replaced by a very benign physical phenomenon where superconducting phases of neighboring segments happen to be equal. That is fine. And when the particles sort of pass through each other, it is not like they slow down. The force happens to vanish at that instant, but they don't necessarily slow down. Yeah, I will comment more about this in a moment. And there is one more thing which we should comment on. That is that because the superconducting metallic segments are along a chain, we can label them. This is the first segment, second, and third. So these particles that I have talked about are distinguishable particles, even in the quantum theory. Okay, so these are not these are identical particles because we are thinking of the characteristics of each metallic segment as being the same in isolation, but they are identical, but they are distinguishable. They're distinguished by their location along a chain. Okay, so these are they're identical but distinguishable particles moving on a circle. That is a mechanical system interpretation. Okay, now there are other ways to interpret and obtain this model. I do not know the background of the audience adequately to know whether I should mention this. Perhaps I will simply say a couple of words. This just to see the kind of thinking that physics can involve us in. So I will explain yet another way of getting this three-rotor problem or an n-rotor problem in a seemingly very different way. Okay, just for fun, so you can see a different kind of physics for a moment. So the quantum n-rotor problem also arises from a partial continuum limit of what is called the two-dimensional XY model of classical statistical mechanics. Okay. Now, the XY model of classical statistical mechanics is a lattice model. So you have a lattice here. I have drawn a lattice with the n sides horizontally and m sides vertically. So I've got 1, 2, 3, 4, 5 sides horizontally and 3 sides vertically, and it could extend further. At each side, you got a spin, a two-dimensional spin. So that's basically an arrow that points on the plane. It's of a unit length, you could say. So it's a planar spin at each side of an n cross m lattice. Now these spins interact with each other. We postulate that they interact with each other via nearest neighbor ferromagnetic interactions. What that means is that the interaction energy between the spin at one side and a nearest neighbor side, such as this one or the one to the top above, is given by minus j, which is the coupling constant, strength of the coupling, times the dot product of the spins at the two sides. Okay, so ij stands for the index location of the first side, I prime j prime the second side. You simply take the dot product of those two spin vectors. And as you know, this dot product can be written, if you write each of the spin vectors as in terms of Cartesian components as some cosine theta sine theta, okay, then then you consider theta as the angular direction from some reference direction, then the dot product reduces to a cosine of the difference in angles. Okay, so that is another way in which such a cosine interaction can arise, simply through the dot product of planar spins. Now, one can do some nice trickery. See, this is, as it stands, a model of classical statistical mechanics. So one studies equilibrium properties of such a spin system at some temperature, you might say. But how do you get a dynamical system out of this? Well, you do some trickery. Well, it is possible to start imagining that the vertical direction is some kind of time direction, and the horizontal is some kind of space direction, and that the time has been discretized here in unit steps or something. Yeah, and this kind of reinterpretation is called a Wick rotation, for those who have come across it perhaps in field theory courses or elsewhere. So to make a long story short, it's possible to take this two-dimensional lattice model, do a so-called Wick rotation, that is a passage to, suppose we regard this gap in the vertical direction as a kind of imaginary time. Yeah, this is called a Wick rotation. Then we get the action of the quantum n-rotor problem. Okay. So I'm not giving you the details here, but the point is that it's possible to take a continuum limit in the vertical direction. That is, you let the spacing between the sides in the vertical direction go to 0, whereas horizontal, you keep them equally spaced. You don't move them closer. You let the spacing tau go to 0, the spacing go to 0, and the number of sides go to infinity. Then the vertical direction will become a continuous line, and that will be regarded as time. And in this manner, it is possible to recover this quantum n-rotor problem, where n is number of sides in the horizontal direction. Now, the reason I mentioned this is that this XY model is of great interest in statistical physics, and it displays what is called the Kosterlitz-Thouless topological phase transition. And it is associated with a unbinding of vortex-anti-vortex pairs as the temperature increases beyond a transition temperature called the Kosterlitz-Thouless phase transition temperature. So the way that these spins sort of point can make it look like a vortex. Yeah, they can go round and round. So one can study a phase transition in the system. And to be honest, when I started working on this problem with Himalaya, it was just after this Kosterlitz-Thouless had received they had received a Nobel Prize for their work in this subject, and we were just trying to understand it, and it led us to studying a problem in nonlinear dynamics. So the message from this little excursion is that the problems in nonlinear dynamics, so nonlinear dynamics is really a universal branch of physics which can deal with pretty much any system that comes from anywhere. You go study something in statistical mechanics, look at it the right way, and you may end up with a problem in nonlinear dynamics. Or you go and look at something in low temperature physics and look at it in a particular way, convert it into some mechanical system, and then you have a problem in nonlinear dynamics. So you are all in the nonlinear dynamics section of Bharatidasan University are very fortunate to be getting skills in this subject, because then you can apply it to problems in many places. And it's not restricted to physics either. Okay, so there is some interesting physics in this XY model and the KT transition, which need not concern us for now. Yeah, let me now come back to the three-rotor problem. As Professor Lakshmanan was mentioning, this problem has something to do with particles colliding also, but here they don't collide. So let us relate it to another problem, which is much more familiar to us. So the classical three-rotor problem may be viewed as a simpler variant of the gravitational three-body problem. Okay, so the gravitational three-body problem is one of the older problems of physics, the Sun, Moon, Earth problem, for instance, yeah, or the Sun, Jupiter, asteroid problem. You have three gravitating masses. In that case, the situation is quite different. Each mass moves in a three-dimensional Euclidean space, R3. Yeah, so the configuration space will be a product of three Euclidean spaces, one for each of the celestial bodies, and you have a configuration space like R9. That is to be contrasted with the configuration space which I described to you, which is simply a product of three circles. So in many ways, this three-rotor problem is a simpler variant of the gravitational three-body problem. It is simpler because the number of degrees of freedom is less. Here, each planet or sun can move in three-dimensional space. Each rotor can only traverse a circle. Yeah, so there's fewer degrees of freedom. And also, the particles cannot escape to infinity. Here, the particles are confined to a circle. Yeah. So there is no escape to infinity. Furthermore, the potential does not diverge when two rotors coincide. Yeah, so the cosine of the difference being 0 just becomes 1. Whereas in the Newtonian gravitational problem, you would have 1 by r sun minus r earth. Yeah, this would be the potential. And that has a divergence as the sun approaches the earth or an asteroid approaches Jupiter. Okay, so here the potential is bounded, whereas there the potential was unbounded below. So that leads to a lot of other complications. Yeah. So thus, in the three-rotor problem, particles cannot escape to infinity. Yeah, there is no concept of infinity here, nor can the dynamics produce singularities. Yeah, we have just seen that they can pass through each other freely. However, such singularities can arise in the gravitational n-body problem. Yeah, and perhaps I will make a few comments about that because Professor Lakshmanan raised this question. Let me say a few words about that. There's some very interesting physics and history here. So when two gravitating point masses, so for many purposes, we can treat the sun and the earth as point masses because the astronomical unit is so large that the sun and the earth's sizes are much less than the separation. So if we treat them as point masses, then when two gravitating point masses collide, their relative speed diverges. Yeah, I mean, this is the familiar catastrophe of classical atom when an electron tries to fall into the nucleus. The solution becomes singular at the collision time. At finite time, the projectile can fall into the force center. More generally, a singularity occurs when either a position or a velocity diverges in finite time. So this is what we mean by a singularity. Now, in 1895, Poincaré is a famous French mathematical physicist. Among other things, he also became a politician. I think he even became the Prime Minister of France at one point. He showed that binary and triple collisions are the only possible singularities in the three-body problem. So the three-body problem is a very important, famous, and instructive problem in physics. The two-body problem, the Earth-Moon problem, was studied by Newton and Kepler and their contemporaries, and can be solved exactly. The three-body problem is not exactly solvable. It's a problem that stumped Newton, and he was trying to understand precession of the perihelion of perigee of the moon, and he was not able to get the observed precession. Basically, one has to include the effects of the sun on the Earth-Moon system, and he was trying to do it in perturbation theory, and this problem was understood better by Clairaut in the next generation. Now, much later, 1895, so one can ask, in a three-body problem, is it possible for some singularities to occur? Answer is yes. And he has shown, Panlave has shown, that the only possible singularities are collisions, either collisions of two particles or collisions of three particles. Yeah. However, he conjectured that so-called non-collisional singularities can occur in 4 or more body systems. Okay. So what is a non-collisional singularity? A non-collisional singularity is when a velocity, or let me just read what I've written here, where the separation between a pair of bodies goes to infinity in finite time. Okay, so this is a very peculiar phenomenon where two bodies don't collide. It's not a collisional singularity, but for instance, one of the bodies flies away to infinity in finite time. All right? So this does not happen in the three-body problem, but Panlave conjectured that it may happen with 4 or more bodies. Now, it took nearly a century for this conjecture to be established. In the work of, in the United States, Donald Surrey and Zhihong Jia and Joseph Gerber in the 1990s, who found specific initial conditions for the 5-body and generally 3n body problems where collisional singularities do occur. Sorry, non-collisional singularities do occur. So this is a very interesting kind of phenomenon. So I want to, it has nothing to do with the rest of our work, but I think maybe interesting for you to hear about. So let me describe it. So this is the non-collisional singularity due to Shia. So you have what is, to first approximation, a Keplerian system of 2 masses, okay, going around their common center of mass. So that is, I can call it a binary system. I have one more binary system over here, another pair of masses. So we can call them tight binaries. They're somewhat tightly bound together. Now we have a messenger particle, which is the 5th particle. And initial conditions are set up so that these 2 binaries are in Keplerian orbits, roughly speaking. And the 5th particle oscillates between the 2. So what does it do? This messenger, when it comes near this pair, it extracts some energy from this pair. Okay, so it extracts some kinetic energy from this pair and gets expelled, gets kicked out. Okay, comes close, extracts some energy and gets kicked out. Now this kind of phenomenon was discovered numerically by numerically evolving 3-body initial states. There are situations where a 3rd body approaches a pair, absorbs some of its energy, their energy. Then when you absorb some energy, they will get into an even tighter orbit, right? Because you have taken away some kinetic energy, so they will fall into the potential some more. They will get into a tighter orbit, and this would be ejected. Now, after being ejected, the messenger then goes and meets the other binary and does the same thing once again. Yeah, it goes and collects some energy from this pair, makes them even more tight, and then gets ejected back. But in this process, because of momentum conservation and all, it turns out when this messenger comes back, the binaries get kicked outwards. So each time the messenger approaches a binary, the binary gets kicked outwards. And this is repeated again and again. I mean, this is not done by hand. You just set up initial conditions, let it go. This is what can happen. What happens then is that in a finite amount of time, the messenger makes an infinite number of excursions of growing amplitude between the 2 binaries. Okay, so the binaries are getting farther and farther apart. The messenger is oscillating faster and faster. And in a finite amount of time, the binaries escape out to infinity. In a finite amount of time, each of the binaries escapes to infinity. The messenger velocity also goes to infinity. Okay. So this is a very interesting physical phenomenon that can happen when you have more than 3 bodies. So I hope to have described how this happens, at least in brief. Now, such things are not totally out of the ordinary. They are seen in numerical experiments, certainly. That is how it was motivated. If you take 3 bodies and choose appropriate initial separations and let them go, one does notice that one of the masses can fly off to infinity while the other 2 form a bound system. Yeah, even when the total energy is negative. Okay, so this can happen even with 3 bodies, but just that the third body will reach infinity at infinite time, not in finite time. And the idea was to combine such 3-body problems with yet more bodies to get it in finite time. In astrophysics also, one sees some similar things. There are so-called hypervelocity stars, where one star from a binary, so you have a heavy black hole and a binary. Yeah, so you have 3 bodies, and one has seen where one of the stars from the binary falls into the black hole and the other is ejected at high speed. Okay, so this kind of thing is seen, and it seems to be a way in which nature is able to extract energy from such systems. So these expelled stars can travel with very high velocity, so that's why they're called hypervelocity stars. Okay, so so far I have been just telling you a little bit about the background and related physics of this 3-rotor problem. Now, in the remaining time, I will just tell you a few of the features of this 3-rotor problem. As I mentioned, the problem of 2 rotors, when you go to center of mass variables, reduced it to a simple pendulum. While you can consider also the limit of infinitely many rotors. When we talked about 3 and 5 rotors, 4 rotors, if you consider infinitely many rotors, such a system in a suitable continuum limit can be described by the Sine-Gordon field theory. Okay, so these extremes, that is 2 rotors or infinitely many rotors, are somehow under control. I mean, at least they are understood. Between these extremes, we find that the 3-rotor, or for that matter, even 4-rotor or 5-rotor, has very rich dynamics and provides a non-trivial arena to study periodic, quasi-periodic behavior, as well as instabilities, chaos, and ergodic behavior. Okay, so that is what our work is on, which I will briefly touch upon here. Any questions about what I've said so far? Okay.
Please go ahead.
Okay, fine, sure. All right. So now let me say something about how you actually analyze the system. Now, we regard it purely as a nonlinear dynamical mechanical system. Now, it is convenient to define a center of mass and relative system of coordinates. So by center of mass, I just mean the mean angle. So you have the 3 angles or the 3 rotors. You divide the sum by 3 and call that the mean angle of the 3 rotors. And then you have the angular differences between pairs of rotors. So the difference between θ1 and θ2 I will call as a relative angle phi1, and θ2 minus θ3 I will call relative angle phi2. Okay. So as happens in many such systems, the relative variables evolve independently of the center of mass variable. So this is a common feature. You may have studied it even in the Kepler problem. And it turns out that the relative angles phi1 and phi2 satisfy a system of nonlinear ordinary differential equations that do not involve phi0. Okay, so we have basically reduced the degrees of freedom to 2 from 3. Of course, the dynamics of phi naught has to then be solved separately. Okay, the dynamics of phi naught, it turns out, depends on phi 1 and phi 2. That cannot escape the complications. But as if you are interested only in the relative motion, you can reduce it to a 2 degree of freedom system. You will notice that the equations of motion are very nonlinear. You've got some mr squared phi 1 double dot, familiar kinetic type of the mass times acceleration. And the force on the right hand side involves the sine of phi 1, the sine of phi 2, because these are the relative angles between rotors, and then the sine of phi 1 plus phi 2. So these phi 1, phi 2, and phi 1 plus phi 2 are all the relative angles between, angular separation between rotors. Okay, so there is, of course, a symmetry between 1 and 2. So the second equation can be written down sort of by inspection. So now the relative energy in units of, so by the way, G has dimensions of energy, as you may have noticed, because the potential is proportional to G. So the relative energy, by relative I mean ignoring center of mass motion, the relative energy in units of this coupling G is the only known conserved quantity. Okay, so this is a system with 2 degrees of freedom. Yeah? So it has a 4-dimensional phase space. Yeah, so you got phi 1, phi 2, phi 1 dot, and phi 2 dot. Okay, 4 initial conditions you have to give. In this 4-dimensional phase space, there is only one known conserved quantity, and it can be, this is the relative energy, the energy of relative motion. It can be regarded as a dimensionless control parameter. And here I write the formula for this energy. Because we have gone to these relative variables, it involves phi 1 dot squared, phi 2 dot squared, and also a cross term phi 1 dot, phi 2 dot. And then there is the potential energy that I already described, namely the cosines of the angular separations between the 3 rotors, the sum of those 3. Okay, so this is the one conserved quantity in this conservative system. Now, this system is relatively simple in 2 limiting cases. One, and in 2 limiting situations, the system is integrable, regular. Yeah. So what are these limits? One is, so for that, let me first describe the lowest energy state of the system. This is the ground state. The ground state is the static solution of these equations, these coupled ODEs. You can look for time-independent solutions that basically arise at extrema of this potential. We draw this potential, contour plot of the potential. One finds that it has an absolute minimum at the center of this square. So this square is basically the configuration space. This is phi 1 and that is phi 2. Okay, so phi 1 goes from minus pi to pi, phi 2 goes from minus pi to pi. Yeah, so the configuration space is this square. Of course, the left edge of the square and the right edge of the square are physically identical, as are the lower edge and the upper edge. Okay, so this is the configuration space is actually a product of 2 circles, yeah, which is called a torus, the 2 torus. Okay, now on this square, the ground state is the point at the center where the rotors all coincide, all 3 rotors coincide, and that is the ground state, minimum energy state of the system. There are also a few other static solutions. There are 2 other types of static solutions with energy 4g and 4.5g, and these occur at a saddle point. So there's a saddle point of the potential. That is where the energy is 4g. So that is another static solution. And then there is a local maximum of the potential at 4.5g, and there you get another static solution. Okay, so but coming back to the simplicity of the system in these limiting cases, the system behaves regularly as the energy goes to 0 or as the energy goes to infinity. What is the corresponding dynamics? Well, when the energy is very small, strictly speaking, I mean, precisely it means energy is much less than g, then we simply have small oscillations around the ground state. Yeah, small oscillations around 3 coincidence rotors. And then you will have 2 conserved quantities, which are the 2 conserved normal mode energies. On the other hand, when the energy is very, very high of the system, so by the way, in this case, we have an integrable system because we said we have 2 degrees of freedom and 2 conserved quantity, 2 normal mode energies. So the system is integrable. On the other hand, when the energy is very high, then the potential energy, which I described as being bounded, right? I mean, the potential energy, because it's simply a sum of cosines, of 3 cosines, it's bounded. And therefore, if the energy is very large, most of it must be kinetic. And in this limit, the rotor angles, or phi1 and phi2, become cyclic coordinates, because the potential can basically be ignored. You focus only on the kinetic energy, and physically speaking, the rotors simply rotate uniformly around the circle. Okay, so that is another very simple limit. System behaves simply when energy is 0 or infinity, but interesting things happen in between. Remarkably, certain periodic orbits provide a window into these new phenomena. So what is the interesting things that happen in between 0 and infinity? Now, periodic orbits have been a very fertile place to look for interesting phenomena in physics and in nonlinear dynamics. This goes back many centuries, but it was particularly championed by Poincaré, who realized the deep significance of periodic orbits even in chaotic systems. But let me just recall some things about periodic orbits in the gravitational three-body problem. That is some nice facts that you may want to keep in your mind before talking about three-rotor problem. Now, in the three-body problem, that is 3 gravitating point masses, Euler and Lagrange described some very beautiful periodic solutions. The most famous of these are the so-called Euler collinear solution. Here you have 3 bodies which are always along a straight line. Of course, that straight line itself rotates. So, but the point is, so there's something very interesting in the periodic Euler and Lagrange solutions of the 3-body problem. They all reduce to solutions of the 2-body problem in an appropriate sense. In other words, it is possible to take Keplerian orbits of the 2-body problem and cleverly export them to the 3-body problem. Okay, so this theme we have been able to exploit even in the 3-rotor problem. That's why I mention it. So the Euler and Lagrange solutions, periodic solutions of the 3-body problem, are basically Keplerian solutions in disguise, but with a 3rd body also playing a role. So in Euler solutions, the 3 masses remain collinear. Yeah, so as in this example, with constant ratios of separations. So in this example, the 2 smaller masses, in this case m and m, go around a circle, a fixed circle with the bigger mass at the center. So that the circles are, of course, Keplerian orbits. But you need not be on a circle. There are even elliptical type solutions for the Euler. So here you have 3 bodies, M1, M2, M3, that traverse Keplerian ellipses around a focus, common focus, which is at their common center of mass. Lagrange extended these solutions of Euler where the particles are not necessarily on a straight line. So in the Eulerian solutions, the particles are along straight lines. Yeah, just that the straight line itself rotates, perhaps non-uniformly. In Lagrange's solutions, the 3 bodies are always at the vertices of an equilateral triangle. So this is an illustration of that. Each body traverses a Keplerian ellipse. So I've drawn 3 ellipses here, and the 3 ellipses each go around a common center of mass. So pictorially, the particles would lie at the vertices of an equilateral triangle, but that equilateral triangle itself will shrink and expand with time, oscillate in its size with time. So these are sort of old solutions of 3-body problem, the 3-body problem. There are much more recent solutions of the 3-body problem, periodic ones even. And among these, there's a particularly interesting class which goes by the name of choreographies. So I just want to give you some idea of what these are, choreographies are periodic solutions of, let us say, an n-body problem, equal mass n-body problem, where the n equal masses follow each other at regular intervals in time around a closed path. Okay, so this is a special type of solution called a choreography. It's called a choreography because it is almost like the masses are choreographed to move in a very regular way. Let me show you a picture of such a choreography. Let's look at the choreography that was discovered about a little over 20 years back. This was discovered numerically. 3 equal masses follow each other in equal intervals of time along a curve that is shaped like the figure 8 or infinity. Okay, so this is an exact solution of the 3-body problem, equal mass 3-body problem. There are many more such solutions, and it is not restricted to 3 bodies. People have discovered even choreographic solutions to 21 bodies, 21 equal masses with gravitational interactions. In this case, it's a planar solution. Yeah, so there are many such solutions that one can look for. Yeah, so these are some of the periodic solutions in the 3-body problem, and Poincaré had the insight that these periodic solutions are very plentiful in chaotic systems. I mean, a periodic solution is about as simple and regular a solution as you can imagine, but they turn out to be very plentiful in chaotic systems, and they can encode a lot of information about even the chaotic dynamics. Now, one feature of that I want to mention over here, but before I do that, I want to know how much time I can use, Professor Lakshman, because I'm not trying to, I don't want to go over time.
Maybe 15 minutes.
Okay. Yeah, fine. So, so please feel free to tell me to stop when you feel it is. Yeah, but I'll try to keep to 15 minutes. Okay, so what so inspired by the gravitational 3-body problem, namely the work of Euler and Lagrange, we have looked for periodic solutions in the 3-rotor problem, and we find families of such solutions. When I say families, I mean the Euler solution is not restricted to one circle of a particular radius. Yeah. So similarly here, depending on the energy, we have been able to find families of periodic solutions. These are called pendula and breathers. At all energies, we can find families of periodic solutions, as well as choreographies in the 3-rotor problem. We have found such things. Yeah. So to give an idea, let me describe what this pendulum solution is like. So in the pendulum solution, 2 of the masses, 2 of the rotors form a bound pair, like a little molecule with 0 separation, and the equations reduce to that of a pendulum. Yeah. So they have a bound pair and a third mass, and they do some dance. And there are 2 distinct classes of such solutions: librational and rotational, below 4G and above 4G. So let me describe this in a movie. Yeah, so this is a pendulum solution. It's a periodic solution of the 3-rotor problem. Now the blue colored dot is where 2 rotors have coalesced and formed a heavy molecule, heavier molecule, and the yellow one is the third rotor. Yeah, so you will notice that this is a periodic solution, and the heavier one, the blue one, has greater inertia, so it moves less compared to the yellow one. You will notice the yellow one has a larger amplitude. So this is an example of a pendulum solution. This is a solution of the 3-rotor problem, but it is constructed from solutions of the 2-rotor problem. So that is the nice feature that generalizes what Euler and Lagrange did. That is a so-called librational orbit, librational solution. And it's not restricted to only one solution. You can add some energy and they will oscillate with larger amplitude. If the amplitude keeps growing, then eventually this solution, the rotors can actually go all the way around the circle. Okay, so you make a transition from libration or smaller oscillations that don't traverse the whole circle to larger amplitude oscillations where they go all the way around the circle. Okay, so these are a pair of examples of periodic solutions. There are many more. Now I want to, I won't discuss the other ones because I want to display some very interesting properties of these pendulum family of periodic solutions. As I said, so the pendulum family of periodic solutions exists for any energy. Yeah. So if energy is less than 4, they are librational, and energy is more than 4, they are rotational. Now, if you are given a periodic solution of some system of equations, one can ask whether it is stable or not. Okay, so there is a procedure to determine the stability of a periodic orbit. Basically, what you do is you take a periodic orbit. I'm drawing it here. We make a small perturbation around that. We start at a nearby initial condition and evolve that forward in time. You ask whether it sort of remains nearby after one orbit, for example, after one time period, or maybe it simply goes away. Yeah. Based on that, by basically linearizing the equations of motion around a periodic orbit, one can determine whether that periodic orbit is stable or not to small perturbations. Okay. Now, a figure of merit of that stability is what is called the trace or the stability index, which is the trace of the so-called monodromy matrix. So the monodromy matrix is a way of encoding how this small perturbed trajectory behaves after one time period of the original trajectory. Okay. Now, there is a way to calculate this stability, and if the stability index, which we need not go into now, let me call it sigma here, if that stability index exceeds 2 or is below -2, then the original solution is unstable. Okay, so this is the theory that comes from studying this monodromy matrix. Basically, you have to study the eigenvalues of this monodromy matrix. If the eigenvalues are somewhat big, then the perturbations will grow. If they are small in magnitude, then the perturbations will oscillate. Yeah, so there is a way to check whether a pendulum solution is stable or not. Now, as I told you, there are many pendulum solutions, one for each energy. So what we did is that we found out whether the pendulum solution at energy E is stable or not by computing its stability index. Here we have plotted it. What we find is that at low energies, so this is energy 0 roughly speaking, at low energies the pendulum solution is stable because the stability index lies between 2 and -2. It is stable. Yeah, but the stability index is not a constant. It changes with energy as you change from one pendulum solution to the next. Yeah. And then at a particular energy, the stability just about becomes marginal. The stability index reaches -2. It doesn't go unstable. It just touches there and then comes back up. But then something interesting happens at a particular critical energy E1. One finds that the pendulum solution goes unstable. Now, okay, you increase the energy of the pendulum solution some more. It remains unstable. Then all of a sudden, it again becomes stable. Now, this pattern is repeated again and again. This is a remarkable phenomenon where the stability of a family of periodic solutions varies with a parameter, here the energy, and there is a sequence of stability transitions, and these stability transitions accumulate geometrically at the energy 4. So this is E equal to 4. So I claim that these pendulum solutions suffer infinitely many stable to unstable, unstable to stable, stable to unstable, unstable to stable transitions, and these transitions accumulate at energy 4. Okay? So this is a very intricate phenomenon, but it is not altogether unheard of. Such transitions in stability have been seen elsewhere. Perhaps the most familiar to us is in a fluid. One may have encountered that a fluid may be flowing in a laminar fashion very smoothly, very regularly, and if you make a small perturbation, it retains its regular motion. But then as you increase the speed of the fluid, increase the Reynolds number, the flow becomes somewhat unstable. It makes a transition from laminar flow to maybe some kind of steady flow to some kind of periodic flow. And then when you increase the Reynolds number some more, there's some further change in behavior that is seen, and eventually the flow becomes turbulent. Okay, so it is believed that the path from laminar to turbulent flow goes through perhaps some transitions, some things called bifurcations, and there may be several such bifurcations between laminar and turbulent flow. So that is perhaps the most grand example of such things, but they are also seen in more modest systems with fewer degrees of freedom. If you have heard of the Henon-Hiles system, that is again a system that came from astrophysics. There again, one has an accumulation of stability transitions. They also occur in Yoshida's two-dimensional anharmonic oscillator, and perhaps closer to home, they occur even in the logistic map. So if you have studied the logistic map, xn plus 1 is equal to r times xn times 1 minus xn, I think. Then as r increases, you have a sequence of period doubling bifurcations, and at some critical value of r, eventually the system becomes chaotic. Okay, so we are seeing something similar here, not in a map, but in a continuous time dynamical system. The same phenomenon also occurs when you decrease the energy from rotational regime down to energy 4. So at energy 4, there is an accumulation of bifurcations or stability transitions. Okay, so I'm going to stop very soon. And what we find is that this cascade, this is called a cascade of stability transitions, is associated with a rather sharp transition to chaos around energy 4G. So this transition to chaos, I will just describe it through some pictures. One can look at what are called Poincare sections for this system. And at low energies, what one does is, since the phase space is four-dimensional, difficult to visualize, you draw a two-dimensional surface through this four-dimensional phase space, fix the energy, and look at orbits at that energy and how they intersect this surface. You record all the points of intersection of one trajectory. Then you take another trajectory, record all points of intersection, and so on. You develop what is called a Poincare surface of section plot. And at low energies, those plots look very regular. In other words, all the trajectories intersect this surface along essentially one-dimensional curves. Okay, so that is a hallmark of regular motion. But as the energy approaches 4, one notices that the situation becomes more complicated. The Poincare sections cease to be concentrated on one-dimensional curves. There are still lots of one-dimensional curves which correspond to quasi-periodic or periodic orbits, but there are also regions of chaotic orbits. There are chaotic orbits which explore two-dimensional regions within the Poincare surface. Okay? And as you reach energy 4, these chaotic regions expand and there is widespread chaos, which you see in this figure. Periodic orbits still remain, and for example, the choreography periodic orbit cuts this section at this point. The pendulum one cuts it here, and other periodic orbits are very much there. In fact, one believes that even in the presence of all this chaos, there are infinitely many chaotic orbits which are even dense within this. But nevertheless, one also sees that this transition to chaos is also associated with certain breaking of symmetries. That is a very interesting phenomenon. This left-right symmetry,
that is, if an orbit intersects this surface over here, it should also intersect over there. At least that is what one finds at low energies. This color is replicated there as well. However, as you approach the transition to chaos, this left-right symmetry is lost. There are orbits that intersected solely on the right side and solely on the left side. Okay, so this there is a spontaneous breaking of certain symmetries which are associated to the transition to chaos. This is again something that may be familiar to you if you have studied fluid flow. If you have fluid flow past a cylinder at low speeds, the flow is laminar and up-down symmetric. But as you, and also left-right symmetric at very low speeds, but as you turn up the speed of the flow, one finds that the flow ceases to be up-down or left-right symmetric. It develops asymmetries. So this is a reflection of similar phenomena, but in a quite different conservative system. So the message is that in this system, there is a rather sharp transition to chaos, and that can be slightly quantified here. I have plotted here the fraction of, as a function of energy, the fraction of the phase space on a Poincare slice, fraction of area of the phase space consisting of regular orbits that or chaotic orbits. Okay, let us look at the fraction of chaos here. So the fraction of area of the phase space occupied by chaotic orbits is essentially 0 up to energy 4. Yeah, up to energy 4 it is essentially 0, and then there is a sharp rise, a relatively sharp rise, and the fraction of phase space occupied by chaotic orbits shoots up and eventually reaches nearly 1. In fact, we find a small band of energies between 5.3 and 5.66 where the fraction of chaos is essentially 1 to the accuracy that we can understand. So in other words, in this system, we find also a band of global chaos in a band of energies. And we conjecture that in that band of global chaos, which is pictured in these figures here. So this is energy 5.1. You see substantial portion of the phase space is covered by chaotic trajectories, and within the band of global chaos, at least to one's eye, practically the entire phase space is filled up by any one chaotic orbit. And you go to slightly higher energies, some islands of regularity open up. Okay? But in this regime of global chaos, we would conjecture that the system begins to display ergodic or mixing behavior. So this is, in this regime, the chaos is sort of maximal, and statistical mechanical treatments may become valid. Yeah. So I think I have used up all my time. My intention was only to give you a flavor of the sort of ideas that are used here and the background. So let me stop here and ask Professor Lakshmanan if there are any questions.
Yeah. So thank you very much, Govind, for a very beautiful talk. And for the audience, if there are questions, comments, you're welcome to ask. Anybody has any questions? So students, or well, in any case, I have several questions coming up because you have shown, you have covered so many things, but I will try to ask just a couple of them. Well, I'm the kind of chaotic attractors, periodic and chaotic attractors you are showing, I think there was a separatrix to start with as you increase the energy. Yeah. Mm-hmm. So you have a separatrix. Around the separatrix, chaotic orbit starts emerging as you increase energy towards E = 4. and then it fills up and so on. I think a similar phenomena occurs in the Duffing oscillator without damping, but external forcing, periodic forcing. As you are showing your figures, I just tried to look at my book on nonlinear dynamics. I see similar symmetric periodic orbits, and then there is a separatrix. Around the separatrix, chaos emerges and fills up slowly the whole phase space and so on. So there are other interesting systems where similar structures emerge, and yeah, you can have a look at them.
Sure.
And so, are you finding any exact periodic solutions in these
Yes.
regimes?
So the ones I mentioned, this what I call the pendulum solution. We have an exact formula for it in terms of Jacobian elliptic functions.
Yes.
Yeah. So in principle, we can write down a formula for it, and that's not the only one. We also have what we are called breathers, or and I have a movie of a breather solution just to show you the kind of thing how that looks. So this is a breather solution where one of the rotors is at rest and the other two kind of oscillate around it. Again, we have got exact solutions for this family as a function of energy for all energy. So indeed, we do have exact solutions, and what we would like to do is to understand the monodromy matrix for perturbations, the stability of these also in an exact way. So far, we have been able to understand it numerically, but we are hopeful that through some Lamé functions, Lamé equations, it may be possible even to understand the details of these stability transitions analytically. Some features we are able to capture, like the accumulation of these transitions. There is a periodicity in this. The distance between successive transitions approaches a constant, just like in the logistic map. So that is one of the Feigenbaum exponents. There's some analog of that here as well.
Perhaps there are connections with conservative maps rather than logistic map. Perhaps you may like to have a look at conservative maps. Because the conservative system, so it's likely that you will have connections with such conservative maps, and this accumulation problem of bifurcations may have similarities there. But anyhow, very interesting work, excellent work. So, anybody has any other comments? Any of the students?
Sir, hello, sir. Am I audible, sir?
Yes.
Yeah.
Sir, actually, you talked about that two binary system, and
yes,
and like separated by some distance, and there was a masses kind of. So the masses was oscillating between two binaries, right?
Indeed.
So physically there was a kind of force was given, and that's why it was oscillating.
No, this is not an external force. This is a force. See, there are 5 masses. You can think of these as 5 planets, just that they are arranged in a somewhat funny way. There is no external force. There are 2 planets which are in a Keplerian orbit around each other. There is another 2 planets which is another Keplerian orbit around each other, somewhat far separated. Okay? Now there is a 5th messenger planet which goes between these 2 by and large, and it is attracted to this pair purely through gravitational attraction. And it's attracted to the other pair again through gravitational attraction. So the forces are purely interparticle gravitational attractions.
Okay, so the gradually that radius of that circle, the orbit will decrease, right, sir? There.
Indeed, yeah. If one body is extracted from a pair, then it carries away some kinetic energy, and therefore the other 2 have to reduce their energy, and so their separation will reduce. Indeed.
Okay, sir. And you are also telling that the separation between those 2 binary will continuously be increasing.
Indeed, that's also true. Basically, it is a kind of a recoil phenomenon. When a binary kicks the third body away, the kick makes them also go in the opposite direction, and therefore the binary that is, let me draw it horizontally. So when this third messenger is kicked to this side, these also get kicked to the right, and then they, of course, at the same time they're going around each other. And then this one goes there and does the same thing to the other pair. It basically extracts some energy, kicks them away, and comes back. And there is no external hand moving this. The dynamics is completely through gravitational interparticle interactions.
Actually, sir, I was thinking of such model for one problem, like my problem. Like if there is a pulse, like two pulses which are like they are connected by some kind of force, like two bounded pulse, we can say, and they are oscillating somehow. So there will be a sharing of energy continuously. So that oscillation we can think of like fifth messenger masses, and the binary we can think of the two binary stars, or they are orbiting. So we can think of as a frequency omega 1 for a one pulse, and second also we have another binary that would have one frequency of rotation. So we can think of frequency of omega 2. So in that way, for like modeling such kind of system can be used. Am I able to convey, sir, what I'm?
I got a rough idea. Yes, I just did. I hope there are at least 3 degrees of freedom here. You said you have 2 pulses. What is the third degree of freedom?
So the oscillation between the pulses.
Okay, you mean kind of the separation between the pulses, is it? Okay. So
yes.
The pulses themselves have some kind of internal dynamics or their own frequencies, and then there is some third frequency that is between the two. Okay. Yeah, I mean, I get a rough idea. I've not looked at your system. Perhaps it may help to think along these lines. Yeah, of course, I would need to understand the details of that to be able to say something more clear. I mean, the essential thing is also what kind of interactions there are between these 3 degrees of freedom. That's very important. I mean, here the gravitational interaction plays a central role in the way that one body can be attracted, extract energy, and then be repulsed. That is something rather special to this situation. If the interactions are different, you may have different phenomena. But I think you may be on the right track in thinking of it as 3 interacting degrees of freedom, and perhaps you can make progress by thinking of 2 of them as being more strongly coupled to each other, and the third one as a kind of arbiter or some kind of messenger between them. Yeah, some thought like that may be helpful in your problem.
Yes,
yeah,
sir.
so Prasant can discuss through email or directly with Govind later on.
Okay,
further.
sir. Okay, sir. Actually, sir, it is your work. Like it's related to your work also. Like 2 fundamental soliton are bounded. So they can be bind together, and you can see some oscillation kind of thing. That's what I was trying to discuss, sir.
Yeah.
So,
Okay,
sir. Okay. Thank you, sir. Yes, sir.
Yeah. Any other questions or comments from students? So what is the status of quantum problem, Govind?
So we have initiated the study of spectral statistics. Of course, this system is not classically, it is chaotic only in some intermediate energies or intermediate values of coupling. So in the quantum problem, we have not yet finished, or even we're only midway through this work. So we've been able to set up the problem so as to compute energy levels. And we are in the process of understanding the spacing distribution. But the preliminary result is that the distribution of spacings does not follow the Wigner surmise. There is a large excess of closely spaced levels. And of course, the whole thing depends on the value of the coupling. So there is going to be some kind of I mean, it is not a purely Wigner-Dyson statistics by any means.
There are several intermediate statistics like Brody statistics and other things. So perhaps it will
And there seems to be a large excess at zero spacing. The zero bin has there's something called the Schnirelmann peak, perhaps that is playing some role over here. But this is still early days, I think. And we are not even able to describe it entirely through the Brody distribution either. But I hesitate to say anything very categorical here.
Okay.
Yeah.
Okay, nice, excellent. So we have enjoyed a very beautiful lecture today, and so let me conclude by thanking Govind profusely for agreeing to give a lecture in this forum, and all of us have enjoyed. So once again, thank you very much, Govind, for this beautiful evening, beautiful lecture. Thank you very much.
Thank you very much. Yeah.
Thank you. Bye.
And bye-bye. Thank you. And all the best to all the students and other participants.
Okay. Thank you. Yeah, we can leave then now. Okay.
Okay.
Thanks. And I think Sendil Velan will take care of other things. He will contact you later.
Okay. Thank you so much. Yeah.
Thank you.
Really appreciate your questions and suggestions.
Bye.
Yeah.